Hello, and welcome to Empowered Learning. This is the second portion of the video on radical expressions and expressions with rational exponents. So we want to start here by just calculating some simple square roots and other nth roots as well. And the purpose of this particular exercise is to make sure that, of course, we know what our square roots are, and as well as some of our familiar cube roots and fifth roots. But we also want to be able to know when we can and when we cannot take the nth root of a particular number. Okay? So we'll start off by noting that we know that 121, the square root of that is just 11, because 11 times 11 is 121. The square root of 81 is 9, because 9 times 9 is 81. Square root of 36 is 6, because 6 times 6 is 36. We also know the square root of 16 is 4. For the answer for E, we know that since we have a negative on the outside of the square root sign, then that's just like multiplying the number square root of 4 by a negative 1. So we put a negative there, and then we know that square root of 4 is just 2. So the answer is a negative 2. And so in this instance, we can actually have a negative answer there. Square root of 25 is 5. For E, we see that we have the cube root of 64, meaning what number can we multiply times itself 3 times to get 64? The answer to that will be 4. Okay. The fifth root of a negative 32 is going to be a negative 2, because negative 2 multiplied times itself 5 times is a negative 32. And so the cube root of a negative 27 is a negative 3, because again, negative 3 raised to the third power, or negative 3 multiplied times itself 3 times, is negative 27. Okay. Moving on to our next set here, we see that we have the cube root of negative 1000 is negative 10, because of course negative 10 multiplied times itself 3 times gives us a negative 1000. For square root of negative 1, we know that it is no real number solution here, because we cannot take the even nth root of a negative number. If we were talking about complex numbers, we would say that this would be I, and that's how I is defined within complex numbers. But if you're not dealing with that, then of course the answer to this would just be no real number solution. Okay. Same for here, no real number solution here as well, because here we have an even nth root, and we cannot take the even nth root of a negative number. Okay. So for our example K, we see that we have square root of m squared, and since we don't know what m is, we know that whatever it turns out to be, it needs to be the absolute value of m. So that came from one of our rules that we talked about earlier in part 1, and if you didn't check that out, and if you need to, please do. So came from this particular rule here. For our next one, we notice here that the fifth root of y raised to the 15, what I've done here is I've rewritten y to the 15 as just y to the 3, all of that raised to the fifth power, because this is the same as saying y to the third being multiplied times itself 5 times. Okay, and so from that, we see that here, if we have 5 of these y raised to the 3 inside of the radical, this tells us how many of the y raised to the 3's we have to have in order to pull out one. Okay, so that's one way that we can think about it. Another way that we can think about it, which is probably an easier way, is to say that y, the fifth root of y raised to the 15 can be rewritten as y raised to the 15 divided by 5, which is the same as y raised to the 3. Okay, so that's another way of thinking about that as well. Here, the square root of t raised to the 44, which means if we have t raised to the 22, we have 2 of those under the radical. There's an understood 2 here. So for every 2 of the t raised to the 22s we have, we can pull 1 out. Okay. And again, another way of thinking about this is we could say this is t raised to the 44 divided by 2, which we know 44 divided by 2 is 22. Okay, so we can look at it that way as well. All right, so now what we want to do is use the product and quotient rules that we talked about in the first part of this video series to be able to simplify each expression. Okay, so here we use the product rule. We know that 16 times n, if we take the square root of that, that could just be square root of 16 times square root of n. And we know that square root of 16 is just 4, so that would just be 4 times square root of n. Okay. For example B, we see that we just split up the 7 and the square root of 7 and the z raised to 16. Do the square root of each. Square root of 7 is irrational, so we just keep it that way. Square root of z raised to the 16, you could either split it up like how I've done there, or you could understand that this just is understood 2, and that would be z raised to the 16 divided by 2, which is z raised to the 8th. Okay, and so you see how we get our answer there. For this next one, we'll say this is cube root of 5 times cube root of b raised to the 9. And so here doing it like this, of course I could rewrite b raised to the 9 as b cubed, all that raised to the 3, or I could just simply say b raised to the 9 divided by 3 and just say that this answer is cube root of 5 times b raised to the 3. And of course, cube root of 5 is an irrational number. Can't break that down anymore, so we just leave it as is. The reason that we know it's irrational is because we know that 5 is a prime number. So there isn't anything that we can factor 5 into that would be identical to 3 times to be able to come up with some nice simple number. Okay, so that's how we know there's nothing else we can do with it. Okay, all right, so let me clear this up, and then we'll go ahead and move on to the next example here. So for square root of b raised to the 5 here, notice that for this one way that we could do this is we could look at this as b raised to the 5 divided by 2, okay? But of course that really doesn't help us to be able to break this down some. So what we could do is look at it this way, rewrite 5 over 2 as 4 over 2 plus 1 over 2, and then use our exponential rules to rewrite like this. Okay. And then from here we know that we have b raised to the 4 divided by 2 is just b squared, and we know that b raised to the 1/2 is just square root of b. And so from there we know that our answer is just going to be b squared times square root of b. Okay, and just write the little equal sign there. So that's one way we could look at that particular problem. Another way that we could look at it is we could rewrite b raised to the 5th as b squared times b squared times b. And then since we know we have an understood 2 here, for every 2 things we see that are like under the radical, we can pull 1 out. And then what's left there is, of course, the b. So that's another way that we can look at example D. All right, moving on. Here we could look at Using this same kind of scenario here, we can take square root of a cubed and say this is going to be a square root of a squared times a, which means we could break it up and do like this. And so now we know that square root of a squared, not knowing what a is, would have to be absolute value of a, times, we know that square root of a can't be broken down anymore, so we just leave it there. Okay. For example F, we see now that it's starting to get a little bit more complex. And so here we're wanting to break up cube root of 54ab raised to the fifth. That's cube root of 54 times cube root of a times cube root of b raised to the fifth. And so as you see here, I've taken 54 and broken it down to its prime factorization. And I see that I have 3 factors of 3 on the inside. So for every 3 of something that I see like under the radical, I can pull 1 out. So that's where this 3 comes from. And from there, we just have 2 left under the radical. So we just write this as cube root of 2. For this next one here, there's only one a under the radical, so we have to leave it as is. And for b raised to the fifth, we know b raised to the fifth could be rewritten as b cubed times b squared. So we have b cubed, which is the same as b times b times b. So we have 3 b's that are inside or under the radical, so we can pull 1 out. And then we have 2 more that are left under there, so we can't really do anything else with those, so we gotta leave them under. And so now everything that is outside of our radicals, we multiply together. So that's why we have 3b, and everything that is inside our radicals, we multiply those together. And that's why we have 2ab squared inside of the cube root. Okay. So in looking at that, we'll go ahead and do our next example here after I clear this up right fast. So let me let's get rid of some of this right here. Give us a little room. All right, so here let's go ahead and move on to the next example. So here we'll take the 5th root of 96 times the 5th root of a raised to the 8. Okay, and so here we need to know, all right, well, how does 96 break down? Okay, so one of the things that we know is that 96 is divisible by 3. So if we take 96 and divide it by 3, we should get 32. So we know that's going to be 3 times 32. Okay, but 32 is 8 times 4, so we'll just do that. And actually, a better way to do this is we know that 32 is 16 times 2. So we'll just say this. Okay, so 96 is basically 3 times 32, or another way, 6 times 16. Okay, so we could look at it that way. Now, if we look at the 5th root of a raised to the 8th, we know that a raised to the 8th means that we have a multiplied times itself 8 times. So here we got 5 of those we can put together, plus another 3 that has to stay separate. Okay, and so from that, what we can do here to close us out, we know that 16 is just 2 raised to the 4th power. And of course, 2 raised to the 4th power here, along with another 2, that would be the same as having 2 raised to the 5th power times, here we have 5 A's. So for every 5 A's we see, we can pull one out, and we just have A cubed left. And here we have 5 2's, so for every one we see, we can pull one out. So we just have 2 here. We have A, and that's what's on the outside here. And then what's left on the inside of the 5th root would be a 3 here and A cubed there. So that's 3A cubed. And so that would be our final answer there. Okay. All right, so moving on to our next example here. We have cube root of 48, x cubed, y to the 8th, z to the 7th. Okay, so here we have cube root of 48 times cube root of x cubed times cube root of y raised to the 8th times cube root of z raised to the 7th. Okay? And so now, if we look here, we'll need to be able to break down 48. So let's see if we can go ahead and do that first. So we know 48 is just going to be 6 times 8, and we know 6 is 2 times 3, and we know 8 is 2 times 2 times 2. So we got 1, 2, 3, 4 2's, 1, 3. Okay, so we look here, go ahead and erase all of this again. So that's 2 times 3 times 2 raised to the 3rd power there. So we see here that we could rewrite cube root of basically 2 raised to the 3rd power times 6. So we say 2 raised to the 3rd power times 6. Keep that on the inside there. We see that we have x cubed under the cube root here. So the answer to that will just be x, and we know because this is x times x times x, so for every 3 x's we have under a cube root, we can pull one out. We can also look at this as cube root of x cubed is just x raised to the 3 divided by 3, which is x raised to the 1, which is just x. So we can also look at it that way, okay? All right, so let's get rid of some of this so that we can have some room to do some other side work. So now, if we look at y raised to the 8th, the cube root sign, we know that we could do this as y cubed times y cubed, and that's 6 other y's. And then we have another 2 other y's left over. And then for z raised to the 7th, so the same thing, we could have z cubed times z cubed times z. And so looking here, we know that we can take the 3 2's that we see right here and pull one out. Leave cube root of 6 on the inside, x. We have 2 of the y cubes that we see there. So for every 3 y's we have, we can pull one out. So we have 1 y with this first one, another y with the second one, and then we keep the y squared in the cube root for the last one. Okay? And then similarly here we have z cubed. For every 3 z's we see, we pull one out, so we have z times another z, and then we just keep the last z under the cube root sign. Okay? And so now we're in a position to where everything that is outside the cube root, we multiply together. Everything that is inside the cube root, we multiply together. So we have 2 times x times y, so that's 2xy squared. And then, of course, the two z's, that would be z squared. And then for the cube, the expressions under the cube root sign that have to stay, we have 6, we have y squared, and we have z. And so this would be our final answer for that. So now I'll go ahead and erase this, and then that'll leave us some room to do some of the other examples we have. All right, so moving on to our next set of examples here. We're going to be using the quotient rule here. So we know that square root of w divided by 36 is going to be square root of w divided by square root of 36. We know square root of 36 is 6. And since we don't know what w is, we have to keep square root of w as is. So we have to treat it like w is prime and thus can't break it down anymore. Okay. Same rule here. We will change this to square root of 9 divided by square root of 144. We know that square root of 9 is 3 because 3 times 3 is 9, and square root of 144 is 12. And so when we reduce that, we know 12 is 3 times 4, and this reduces to 1, and we have 1/4 as our answer. So in example K, we see that square root of 50 can be rewritten as square root of 25 times square root of 2. And we see that square root of 2's in the numerator and denominator reduce to 1. And thus, we just have square root of 25 left, which equals 5. For our next example here, we see that we have cube root of negative 27y raised to 36 over 1,000. So using the product and quotient rules, we can rewrite this as square root of negative 27, cube root of negative 27 times cube root of y raised to 36, all divided by cube root of 1,000. And so we know that cube root of negative 27 is negative 3. The cube root of y raised to 36 can be rewritten as 36 divided by 3 as far as the exponents are concerned, which gives us y raised to 12. And then the cube root of 1,000 is just 10, because 10 times 10 times 10 is 1,000. So this is our simplified form for that. So for our next example here, we know that we could rewrite this as cube root of a raised to the 4 over cube root of 125. We know that here a raised to the 4th can be written as a raised to the 3 times a. And we know that for cube root of 125, we know that the answer to that is just going to be 5, because we know 5 times 5 times 5 is 125. So the way that we could possibly rewrite that is like this. Okay, so now from here we have this, split it up like that, and we rewrite the bottom as 5 raised to the 3 divided by 3. And I'm just doing this just to show you alternative ways. If you know that this is just 5, you can just write that it's just 5. Okay, so that's essentially what I'm going to do here. And for cube root of a cubed, we know all this is just a. So we just have a times cube root of a, all that divided by 5. And of course, here I could have took cube root of a cubed and rewrote it like this, which would have gave me a to the 1, which would have gave me a. That's why I had that bit. Okay, so for our next example, we have the 4th root of x raised to the 7th over the 4th root of y raised to the 8th. And so for our denominator, we could just rewrite this as y raised to the 8 divided by 4. For the numerator, I could say this is fourth root of x raised to the fourth times x raised to the 3. We know that fourth root of x raised to the 4. Take that. We know the denominator here is y squared, and we'll take fourth root of x cubed there. Okay. And so from here, we know that fourth root of x raised to the 4 will just be x. Okay. Now, the question here is it going to be x or is it going to be absolute value of x? Okay. So we can answer that question right now by saying following. So here we do, if we rewrite this as x squared times x squared, and of course this would just be 4x is being multiplied times each other. I'm sorry for that not looking so good. If you notice here that we don't have the situation of this. And so this is the only time we were told that we had to do absolute value of x when we don't know what x is. Since we have a fourth root instead of a square root, we can just answer this and allow it to be x. If I can get it to act right here. So we don't really need this as absolute value of x. It could just be x. So now let's get rid of this stuff. And so now all this will just equal x times fourth root of x cubed. And of course, our denominator here will just be y squared. Okay? So that would be the simplest form for this particular radical expression. And of course, for our last one here, we have cube root of a cubed times cube root of b raised to the 4 all over cube root of 64. Okay? And so we know here that cube root of a cubed could just be a. Cube root of b raised to the 4, we have 3 b's in there, so we can pull one out, and we just have one left under there, so that is why we could just write that as b under here. And cube root of 64, we know that that's just 4, because 4 times 4 times 4 is 64. So rewriting everything, this would be our final answer. Okay. So this concludes part 2 of the series of videos on radical expressions. We'll continue on with more examples, utilizing more of the rules that we talked about in part 1 of this video series in the next video.